Hello, dear students. We are back again with another video lesson. Today's lesson, we are going to explain chapter 6 about the electricity and microfarad. So in the previous lesson, we covered chapter 5, and today's lesson, we are moving on to chapter 6, a very important chapter. So in the Wizari exam, the questions from this chapter typically carry about 20 or 24 markers. So let's dive into it with the full focus. Before we get started, chapter 6, I would like to tell you some brief about this chapter. In this chapter, as you can see here, we have 3 sections. Section 1 about the electricity from magnetism. So we have 3 topics in this section: electromagnetic induction. Okay, how can we induce the current and electromotive force? And the second topic, characteristics of the induced current and cell of induction. In section 2, we will talk about the generators, motors, and mutual inductance. So in this chapter, in this section, also we have 3 topics: generators and alternating current, motors, and mutual inductance. In the last section in this chapter, a very good section, AC circuits and transformers. We have 4 topics in this section: effective current, applying Ohm's law to AC circuits, transformers, and energy transfer. So let's get started with the section 1 in chapter 6. Electromagnetic induction. So we have some information and some knowledge for the students, very good to know. The definition of resistance states that current in a circuit is proportional, according to Ohm's law, current in a circuit is proportional to the applied potential difference and inversely proportional to the resistance. Guys, according to Ohm's law, V is equal to what? V is equal to IR. I in the circuit is equal to what? V over R. Okay, and sometimes we can represent, and instead of V, you can write down epsilon. This epsilon, it means that the potential difference and voltage across the circuit, okay? Divided by R, it doesn't matter to write V or epsilon, the symbol. So the amount of the current is directly proportional to the potential difference, but inversely proportional to the resistance. Okay, inversely proportional to the resistance of the circuit. Electromotive force, potential difference, produces an electric field that this EMF produces, its current produces the electric field that causes of the force on a free charge. Okay, if you remember, in a magnetic force on a current carrying wire, when the current passing through the conductor, this current produces a magnetic field. Okay, so if the current into the wire is placed into the magnetic field, so this magnetic field exerts a magnetic force on the conductor. This magnetic force separates the negative charge and positive charge. So in this way, we can induce electromotive force and induce a current in a closed circuit. So it goes force on a free charges in a conductor. This force causes the free charges to move through the conductor. When this charge is moving in the conductor, moving charge produces current, induces current. Why? Because current is the flow of charge per unit of time, Q over T. We studied in chapter 7, grade 11, flow of charge per unit of time. This moving charge are called an electric current. The moving of charge is called electric current. So the current is produced by moving charge, moving free electron in the conductor. A charged particle moving in a magnetic field experiences a magnetic force. Charged particle moving in a magnetic field experiences what? A magnetic force. Okay? So when the particle moves with the component perpendicular to the field, so you can find the magnetic force by using this equation, QVB. So without sign, why? Because when the charge is moving perpendicular to the magnetic field, it's not necessary to write sine 90 because sine 90 is equal to 1. So this is some good knowledge for the students before starting chapter 6. Guys, the first definition in this chapter is electromagnetic induction. In this chapter, in this section, guys, we are focusing on the electromagnetic induction, or how can you induce the current, how can you produce electromotive force. Electromagnetic induction is the process, guys. Is what is the process? So you have to do something, okay? It's the process of creating a current. Process of creating what? Creating current. I. In what? In a circuit loop. By what? By changing the magnetic flux in the loop. So this is very important. Pay close attention. How can we create current in a circuit loop? By changing the magnetic flux in the loop. By changing what? Magnetic flux. So the student, you have to keep in your mind, what is the flux? Okay, if you remember, we studied in chapter 5, section 1. Flux is the number of the magnetic field line that cross the certain area. So, for example, if we have a magnetic field, okay, directed to the right, okay, so this is magnetic field. And now, do we have flux? Absolutely no, we don't have flux. Why? Because we don't have certain area. Without area, we don't have flux. For example, if you put a circular coil, circular conducting coil, into this magnetic field. Now, do we have flux? Yes, of course, we have flux. The number of the magnetic field, how many field lines cross this circular loop? 4. 1, 2, 3, 4. This 4 lines is called flux. Okay, now, do we have flux? Yes, we have it. Okay, now we have flux. Why? Because we have magnetic field and a certain area. Without a certain area, we don't have flux. How can you determine the magnitude of the flux is equal to AB cosine theta? If the plane of the loop is perpendicular, the maximum, the magnetic flux becomes maximum. Okay, why? Because the maximum number of the magnetic field lines crosses and passes through the area, through the loop. So in this way, you can determine the magnitude of the magnetic flux, which is equal to AB cosine theta. If the plane of the loop is perpendicular, area vector is parallel. Okay, so if the area vector is parallel with B, cosine 0 parallel becomes 1, becomes maximum. So that is why flux becomes maximum value. So this is flux. It is very important to know how can we change the magnetic flux. So this is very important. Okay, flux is equal to what? Is equal to A B cosine theta. What does the magnitude of the flux depend on? What does the magnitude of the magnetic flux depend on? The magnitude of the magnetic flux depends on 3 factors: area, magnetic field, and angle between the area vector, plane of the loop, and the magnetic field, or the orientation of the loop. What does magnetic flux depend on? Depend on 3 factors: the area of the coil, the magnetic field of the magnetism or bar magnet, and the orientation of the coil has effective on the magnetic flux. So in how many ways, guys, in how many ways we can change the magnetic flux? How can we change? Look, how can we change, or how can we obtain change in magnetic flux? How can we obtain change in magnetic flux? Change in magnetic flux is delta flux. What do you mean by delta? Change. Okay. In how many ways we can change the flux? By 3 ways. By changing area, by changing magnetic field, and by changing the angle or the orientation of the loop. And by 3 ways: changing area, delta A, changing magnetic field, delta B, or by changing the angle or the orientation of the loop. In these 3 ways, we can produce change in magnetic flux. So the change in magnetic flux is very important, and it has a very good role to induce the current. Without change in magnetic flux, no current, no EMF induced in the closed circuit. Look at this simulation, guys. So it is very helpful for the student to understand easily about the electromagnetic induction. Look at this simulation, guys. Look. We have a loop of wire, a conductor, okay, a conductor loop, and we have a bar magnet, okay, north and south. Do we have magnetic field? Yes, of course. We have magnetic field because we have a bar magnetism, okay. Do we have magnetic flux? Of course, we have magnetic flux. We have flux. Why? Because many field lines crosses the certain area. Okay, so the magnetic field line is that crosses this circle, this circular loop is called the magnetic flux. Okay, but the others is not a flux. Now we have a light bulb and a conducting loop. Okay, a conductor loop. How can we induce the current in this light bulb? Okay, if the magnet is at rest with the circuit, both of them is at rest, do we have induced current? The current is not induced. Why? Because there is no relative motion. There is no change in flux. Do we have change in flux? No, we don't have change in flux. Look. Guys, look. Because electromotive force, according Faraday's law, is equal to what? Change flux per unit of time. What do you mean by this delta? Change? Change in what? Change in flux. In how many ways we can change flux? In 3 ways. By changing area, by changing field, and by changing the orientation of the coil. In how many ways we can obtain change in flux? In 3 ways. By changing area, by changing field, and the orientation of the loop. If there is a relative motion between the magnet and the coil, the current is induced in the loop. Why? Because in the case like for approaching the magnet into the coil, what happened? The light bulb glows. Why? Because by approaching the magnet into the coil, what happens to the magnetic field? The magnetic field gets more increased. When the magnetic field increases, what happened to the flux? Flux also increases. Change in magnetic field, it is that increase or decrease? Both. By increasing or decreasing magnetic field, flux changes. Why? Because change in the magnetic flux, we can obtain change in magnetic flux by increasing or by decreasing. Because change, it means that both decrease or increase. How about in the case, like for example, if we move away the magnet into the coil, does the current induce in the light bulb? Of course. Why? Because by moving away the magnet from the coil, what happens to the magnetic field? The magnetic field decreases. When the magnetic field decreases, what happens to the flux? Flux changes. Why? Because magnetic field decreases, flux also decreases, and so that is why the flux is changing. If there is no change in magnetic flux between magnet and the coil, no current is induced. Okay? For example, if we set the magnet into the coil, guys, look. Now, do we have induced current? No, we don't have. We don't have. Why? Because there is no relative motion. There is no change in magnetic field. There is no change in magnetic field. There is no change in area, and there is no change in orientation. It means that delta flux is equal to what here? Delta flux is 0. No change in flux. If delta flux is 0, what happened? Guys, if change flux is 0, EMF 0, current 0, and the flow of charge is 0. There is no flow of charge. But by moving the magnet into or out of the conductor, the current induced and the charge is moving through the conductor. Okay, and the light bulb glows. Okay, because of the relative motion between the bar magnet and the coil, it goes to change in magnetic flux, and change in magnetic flux in turn induces the current and electromotive force. Guys, how about if we move the coil instead of the bar magnet? Does the current induce the circular loop? Yes, of course. Look, by moving the coil or the magnet, it doesn't matter. Okay, the current still induces in the circular loop. Why? Because we have change in the magnetic field in the case of approaching through the magnetic field or moves away from the magnetic field. Okay, guys. How about if we place the bar magnet near the coil without moving, without relative motion? How can we induce the electric current? By increasing and decreasing the strength of the magnetic field. Look, so here the strength of the magnetic field is 100%, maximum strength of the magnetic field. If we decrease the magnetic field of this bar magnet, what happened to the magnetic field? The magnetic field decreases. When magnetic field decreases, what happened to the flux? Flux changes, also decreases. Okay, so the current is induced. Look, by increasing and decreasing the magnetic field, what happened to the light bulb? The light bulb glows. Okay, why? Because the current induced also by increasing and decreasing the magnetic field without relative motion. Okay, so how about by changing area? Can we get the change in magnetic flux by changing area? Yes, of course. Why? Because magnetic flux, of course, depends on what? Area of the coil, magnetic field, and orientation. By changing area, does the current induce it in the loop? Yes. How? Look. So this is the area of the loop. By increasing and decreasing the area of the loop, what happened to the light bulb? The light bulb start glowing. Okay. Why? Because the current is induced. Why the current induced by increasing and decreasing the area of the loop? Because by increasing the area of the loop, what happened to the flux? Guys, look. Flux is equal to what? A, B, cosine theta. By increasing area, what happened to the flux? Flux increases. When flux increases, can we say it means that flux changes? Yes, of course. So when the area increases, the flux changes here, and the current is induced, electromotive force induced in the loop. So how about if we decrease the amount of the area? Flux also decreases. Why? Because the relation between flux and area is directly proportional. By decreasing the area, the current is also induced in the circular loop. Guys, in this two way, you can induce the current by changing magnetic field and by changing the area of the loop. So how about the angle, the orientation of the loop and the magnetic field? Guys, look. Without moving magnetism, approaching magnet moves toward the coil or away from the coil, or approaching and moves away the coil from the bar magnet, or without changing area, without changing magnetic field, how can we induce the current? By the orientation between the magnetic field and the circular loop. Look at this simulation, guys. We have a bar magnet and we have a coil. If both are constant, bar magnet is constant and the circular loop is constant, the area is constant. In this case, the magnetic field doesn't change, area doesn't change. Okay, area is constant, magnetic field is constant. So what is changes here? Only the orientation between the magnetic field and the circular loop changes. If you open the faucet, what happened? The falling water. Okay, the falling water is caused to the change, the orientation of the magnetic field through this circular loop. So in this way, you can induce the current and electromotive force. This is by what? By changing the orientation of the loop. Okay, so finally, we can say we can change the magnetic flux by three ways: by changing area, by changing magnetic field, and by changing the orientation between the magnetic field and the circular loop. Let's go back to our pamphlet. Okay, we have a question here, guys. Consider a closed circuit consisting of only coil that is in the vicinity of the magnet. If there is no battery to supply a current, how can we get induced current? If there is no battery, how can we get induced current? We have a circular loop and a bar magnet. If neither the magnet nor the circuit is moving with respect to each other, if both of them are at rest, there is no movement between magnet and the coil, and there is no change in magnetic field, there is no change in the area. The strength of the magnetic field is constant and the area is constant, and there is no relative motion. There is no current induced in the circuit. The current does not induce. Electromotive force does not induce. Why? Because there is no change in magnetic flux. Without change in magnetic flux, we cannot create and we cannot induce current and electromotive force. If the circuit and the magnet are moving with the same direction, as you can see in this figure, guys, for the first part, if neither the magnet nor the circuit is moving with respect to each other, as you can see in this figure, both of them at rest. No current induced. Current 0. EMF 0. Why? Because both of them at rest. Like Doppler effect, if you remember. If the observer and the source remain at rest, okay, there is no Doppler effect occurred. Why? Because there is no relative motion between the source and the observers. That is why the Doppler effect does not happen. In the second figure, if the circuit and the magnet are moving with the same direction and the same speed, okay, in the second figure also the current does not induce. Why? Because there is no relative motion. Without relative motion, the current does not induce. Okay, both the circuit and the magnet are moving in the same direction with the same speed. In this case also the current is 0, the induced current, yes. Why? Because there is no change in magnetic flux. Both of them moving with the same speed, same direction. In the third case, when two bar magnets, okay, located side by side, but the south pole of one bar magnet is located near the north pole of the other magnet, even by approaching the magnet, these two magnets toward this coil, no current induced here. Why? Because how many magnets do we have? Two magnets. The two magnets placed side by side with the same pole or opposite pole? Opposite pole. Why current does not induce it even in the presence relative motion between the magnet and the coil? Because the effect of one bar magnet cancel the other bar magnet. Okay, because the effect of the magnetic field of one magnet cancel the other, and magnetic field becomes, the total field becomes 0, and there is no change of the magnetic field. But if the circuit moves toward or away from the magnet, or the magnet moves toward or away from the circuit, it doesn't matter. Both. If the circuit moves toward the magnet, or the magnet moves toward the circuit, or both of them are moving to each other, or both of them moves away from each other, relative the current is induced. Okay, so in the presence of the relative motion between the circuit and the magnet, the current is induced and electromotive force is induced in the conductor. Changing magnetic flux will occur when one or two or all three of these changes, like area of the coil, magnetic field, and angle or orientation, according to this equation. Flux is equal to AB cosine theta. A current results when a closed circuit moves with respect to the magnetic field, as long as there is a relative motion between the circuit and the magnet, and the current and EMF created in the closed circuit. Okay, if the circuit is closed, the current and EMF induced. But if the circuit is open, for the open circuit, only EMF induced. The current does not induce in the open circuit. Why? Because current, it means that flow of charge. Okay, if the circuit is open, like open wire, in the open wire there is no flow of charge. There is no current, like a battery. The battery, we don't have current, only we have a potential difference. So when does we have a current in the battery? When the battery is connected with the closed circuit. In the closed circuit, we have current, but for the open circuit, we don't have current. Only we have a potential difference. What condition is required for current to exist in the circuit? There must be a relative motion between the circuit and the magnetic field. Or when both the circuit and the magnet are at rest relative to one another, charges in the conductor do not experience a magnetic force. If both at rest relative to each other, if both the circuit and the magnet at rest, there is no induced current. Why? Because there is no change flux. There is no magnetic force acting on the conductor. If there is no magnetic force, there is no separation between the positive charge and negative charge. Okay, and the conductor wire do not experience magnetic force, so there is no induced current and no EMF. Guys, be careful. We have many types of the material, like conducting material, conducting wire, and insulator. We have conductor and insulator. In the conductor wire can the electricity can like the current is produced in the conductor wire. But in insulator, there will be no current even in the presence of the relative motion between the conductor, between the insulator and the magnetic field. Why? Because insulator cannot conduct electricity because insulator has no free electrons, but conductor can conduct electricity very easily. Why? Because conductor has free electrons like copper, gold, okay, metal, okay, because they have a free electrons, so that is why they can conduct electricity, okay. By moving a conductor into the magnetic field, can we induce current? Yes, of course. Why? Because the moving conductor into the magnetic field, this magnetic field experiences a magnetic force on the conductor, and this magnetic force can separate the free electron from the outermost shell of the atom, and it goes to moving electron, and it goes to creating current and electromotive force. But by moving insulator into the magnetic field, listen carefully guys, by moving insulator into the magnetic field, no current induces, no EMF induces, but we have magnetic force. Be careful. Why? Because in the insulator also we have a positive charge and negative charge, okay, we have atom. So by moving this positive charge and negative charge into the magnetic field, this magnetic field experiences a magnetic force on the insulator. But this magnetic force that acting on the insulator cannot separate the electrons from the negative charge and positive charge. The magnetic force cannot separate the negative charge and positive charge in the outermost shell of the atom of the insulator. Why? Because insulator has no free electron in the outermost shell. All electrons are fixed in the outermost shell. This force cannot separate, cannot eject the electron from the outermost shell. So that is why the current does not induce in the insulator. But guys, keep in your mind, in both cases, insulator and conductor, by moving insulator and conductor into the magnetic field, in both cases, there will be a magnetic force. But the magnetic force on the current, on the conducting wire, they can separate positive charge and negative charge. But the magnetic force of the insulator, they cannot separate the positive charge or negative charge in the insulator. Why? Because all electrons are fixed in the outermost shell of the insulator. Why is the current generated in a moving conductor? Moving what? Conductor, free electrons, in a magnetic field, but not in a moving insulator in the same magnetic field. So what is the reason? Guys, be careful. A force acts on the charges in both cases. In both cases, the force acting on the charge in the insulator and in the conductor. But in conductors, the electrons are free to move, okay, in response to the magnetic force. A force also acts on the electron in an insulator. The force also acts on an insulator. But insulator, in the insulator, electrons that are not free to move. So that is why the current does not induce it in the insulator. By moving conductor and insulator, by moving conductor into the magnetic field, magnetic force created, and this magnetic force, because the conductor has free electron, it goes to separating electron from negative charge and positive charge, current and EMF induced. But by moving insulator, there will be a magnetic force on the charge, okay? But they don't have free electrons, so that is why this force cannot separate the positive charge and negative charge from each other. So that is why there will be no current, there will be no electromotive force. As long as if the relative motion between the coil, closed circuit, and turn, and the magnet, current will continue to flow through the circuit, through the closed circuit. Okay? Relative motion into the magnetic field, it goes to change the magnetic flux, and change the magnetic flux, it goes to create electromotive force. Electromotive force for both closed circuit and open circuit. By moving open circuit into the magnetic field, does the current induce? No. But by moving open circuit into the magnetic field, potential difference and electromotive force is induced or is created. By moving the open circuit, okay, into the magnetic field, EMF induced? Yes, of course. By moving the closed circuit into the magnetic field, still EMF induced? Yes, of course. In both cases, for open circuit and closed circuit, there will be electromotive force, EMF, in the presence of the relative motion between the magnetic field and the circuit. But current, just for closed circuit. The current induced only for the closed circuit. In the open circuit, we don't have current, we don't have flow of charge, even if it's moving into the magnetic field. The induced electromotive force, EMF, in a straight conductor. So in the straight conduction, sorry. So this is the first equation that you will study in chapter 6, section 1. Electromotive force, EMF, in a straight conduction is equal to what? B L V sine theta. After finding EMF, you can find and determine the amount of the current. Current is equal to what for the closed circuit? EMF divided by what? By resistance. How can you determine electromotive force and current in a straight conduction? By using this equation. EMF for the straight conduction. For what? For straight conduction. Or straight wire. Guys, look. If we have a wire, a conductor wire, okay, and moving into the magnetic field, by moving the conductor wire into the magnetic field, does the current and EMF induces created? Yes, of course. If the wire is open, only the potential difference is created. There will be no current. But if the wire is closed, the current also induced and created in the loop. Like for example, for the straight wire, if you have a magnetic field, the yellow cross indicates the magnetic field into the page. What do you mean by this cross? Into the page, okay? Guys, look. If we have a wire, a conductor wire, what is this? This is a conductor wire, a copper wire, okay? And it has length, we have length. And when the wire is moving into the magnetic field, the wire must be moved. Without move, if the wire is at rest, there will be no electromotive force. Why? Because electromotive force in a straight wire, in a straight conductor, depend on what? Magnetic field. This is magnetic field. And the length of the wire, length of the conductor. And the conductor must be moved. If the conductor is at rest, there will be no electromotive force. There will be no current. But if the wire is moving into the magnetic field, moving wire into the magnetic field, like for example, if the wire is moving into this direction, the EMF is created in this wire. The EMF is created in this wire. So how can you determine the positive charge and the negative charge into this wire? By using right-hand rule, guys. By using what? Right-hand rule. The thumb is represent for the direction of the movement, the velocity of the wire, V. Okay, the thumb is what? The velocity of the wire. The four fingers represent for the direction of the magnetic field as usual. Okay, if you remember, how many forces do we have? Two. Magnetic force on positive charge and magnetic force on the negative charge. Out of thumb is positive charge and here is negative charge. Let's put your thumb into the direction of the V. Where is the direction of the velocity of the wire? Is directed to the east, X positive. Okay, your thumb is in a positive direction, positive X, right. And the four fingers into the page. The upward here is positive or negative. Here is positive. Okay, this end becomes what? Positive, and this end becomes what? Negative. How can you determine the positive and the negative charges in the conductor? By using right-hand rule. Okay, your thumb is the direction of the velocity and the four fingers is the direction for the magnetic field. And we have, as usual, we have two forces, force on the positive charge and force on the negative charge. Okay, as you can see here in this figure, we have a straight wire. The straight wire is moving into the right. Okay, your thumb is into the right. So how about the blue dots? The blue dots indicate the direction of the magnetic field. Dot is out of the page. Okay, the four fingers is out of the page and V is into the right. V, the magnetic field, out of the page, Z positive. V, X positive. Here is positive charge downward and the negative charge is upward. So here is positive charge and here is negative charge. Okay, so by moving conductor into the magnetic field, we can create electromotive force, which is depend on what? Magnetic field, the amount of magnetic field, the length of the conductor, and the velocity and the speed, or the speed of the conductor, but it should be moving perpendicular to the magnetic field. If the wire is moving parallel to the direction of the magnetic field, there will be no electromotive force. How? Look, assume that this is magnetic field. What is this? Magnetic field. Directed to the x positive, okay, to the right. And we have a conductor wire, and it's moving to the right. Both of them to the x positive, okay? So do we have electromotive force? No, we don't have electromotive force. Electromotive force here is equal to 0. Why? Do we have length of wire? Yes, of course we have it. E is equal to what? B, L, V, sine theta. Guys, look. Do we have magnetic field? Yes, we have. We have magnetic field. Do we have length of the conductor? Yes, of course. Do we have the velocity and the speed of the conductor? Do we have a movement of the conductor? Yes. It's moving to the right. But angle, what is the angle between V and B? The angle between V and B, because it's parallel, angle between them is 0, sine 0, 0. So that is why there will be no electromotive force and there will be no current when the conductor is moving parallel into the direction of the magnetic field. Okay? So when does the conducting wire, the straight wire, has maximum value of electromotive force? In the presence of the magnetic field and the conductor and the movement, when the straight wire or the conductor, straight conductor, is moving perpendicular to the magnetic field. If it's moving perpendicular to the magnetic field, the amount of electromotive force becomes maximum, and the amount of the current also becomes maximum value. But if so, another question: when does the electromotive force in a straight conduction has maximum of has half of its maximum value? When the angle between V and B is 30 or 150. Consider a conducting wire A and B pulled through a magnetic field to the right. Okay, the wire is moving to the right. The charged particle moving with the velocity at an angle to the magnetic field will experience magnetic force. According to the right-hand rule, this force will be perpendicular to both magnetic field and the velocity of motion of the wire. For free positive charges in the wire, the forces is directed downward along wire. For the negative charges, the force is upward. Downward positive and upward is negative according to the right-hand rule. The separation of the positive and negative charges by magnetic force creates a potential difference. Creating what? A potential difference between the ends of the wire, and the magnitude of the induced EMF is given by the following relation. EMF is equal to BLV sine theta. So you can rearrange this equation. EMF is equal to what? BLV. B is equal to what? B is equal to EMF over LV. B measured in what? Tesla. The equivalent unit of Tesla. Electromotive force measured in volt. Length measured in meter. Velocity meter per second. Okay, if you rearrange this equation, it becomes what? Volt second per meter square. So what is the equivalent unit of Tesla? We have many equivalent units of Tesla, but one of the equivalent unit of Tesla is what? Volt second per meter square. So this is very important. Be careful. Upon what factor does the induced electromotive force on a straight conductor depend on? Straight conductor. What does electromotive force, EMF, in a straight conductor depend on? It depends on 4 factors. The amount of the magnetic field, the length of the conductor, the motion and the movement of the wire into the magnetic field, and the angle between V and B. So the polarity of the induced EMF, electromotive force, it depends on the direction of the wire is moving through the magnetic field. By reversing the direction of the velocity and the movement of the wire, the polarity of the conducting wire also changes. So we have many different cases. In the first case, where is the magnetic field? Out of the page. The movement of the wire is to the right. Here, down positive and up is negative. Positive and negative. So this wire acts as a battery, as you can see here. Inside the battery, there will be a chemical reaction. So this chemical reaction, it goes to separating the positive charge from the negative charge. But for the straight wire, for the conducting wire, we don't have chemical reaction. How can you obtain the positive charge and the negative charge through the ends, the polarity of the conducting wire? By moving this wire into the magnetic field. The magnetic force that acting on the charged particle separated the negative charge from the positive charge. This magnetic force created the electromotive force and the induced current. But for the battery, as we can, you know that we are using in the calculator or in the many other applications, this battery is the chemical reaction inside the battery provides this separation of the charged particle, the positive and the negative charge. Here, look at this figure. Where is the movement of the wire is directed to the left, X is negative, and the magnetic field still out of the page. Okay, the upward becomes positive and the downward becomes negative. Upward becomes positive and here becomes negative. So how about if the magnetic field is into the page and the movement of the wire is directed to the right? Look, field into the page. Where is the movement of the wire? To the right. Upward becomes positive, down becomes what? Becomes negative. When does the magnitude of the induced electromotive force in a straight conductor has maximum value? When the conductor's motion perpendicular to the magnetic field. When does become zero? If the conducting wire is moving parallel to the direction of the magnetic field. In this way, no EMF is created in the coil. Half of it is maximum value in the angle of 30 or 150. Look at question 8 in chapter review, guys. 2 bar magnets are placed side by side. How many bar magnets do we have? 2. We have 2 bar magnets placed side by side with the same magnitude. North-south, south-north. Okay? And we have a coil of wire. We have 2 bar magnets placed side by side so that the north pole of one magnet, is next to the south pole of the other magnet. Is next to the south pole of the other magnet. Okay? North pole of one magnet is placed next to the south pole of the other magnet. If this magnet are then pushed toward a coil, okay, if the magnet is moving toward the coil, okay, now do we have a relative motion? Yes, of course, we have a relative motion by pushing the magnet into the coil. Would you expect an electromotive force EMF to be induced in the coil? No. There will be no induced EMF. There will be no electromotive force by pushing the magnet into the coil. Why? Because the effect of the bar magnet of one magnet is cancel the other. No, because effects of one magnet cancel those of the other magnet. Okay? So these two fields, they cancel each other. But like sometimes the student asks, what about if the two magnet is located side by side with the same pole? Yeah, by pushing the magnet, the current and induced EMF is created, and the EMF is induced in the coil. If there is a relative motion and B is perpendicular to the motion of the wire, the maximum EMF is induced. If there is a relative motion and B is parallel, EMF is 0. And for standing conducting wire, no motion, no movement, V is 0, and electromotive force also 0. For insulator material, no EMF and no current induced even by moving the insulator into the magnetic field. Because the insulator has no free electrons, but magnetic force acts on an insulator when it moves in a uniform magnetic field. But this magnetic force cannot separate the positive charge from the negative charge. Guys, that's all for today. Thank you for listening. Inshallah, in the next lesson, we are continuing to explain the all topics of the chapter 6, and especially in the section 1 about the the Lenz's law, and the induced current, and the electromagnetic induction. Keep up your best doing. Thank you for listening.